All right, so now we have seen how gradient descent works in principle, right? So we need to find partial derivatives of our loss function with respect to parameter values, and then we do like small steps in the direction minus the gradient, right? So let us see what it looks like in practice. So what if we are to implement gradient descent for linear regression? So here is our, let's say for simplicity, we have just one variable. So we have one variable linear regression, which means that our beta is a vector with two entries, right? So when we find, it means that the graph of our loss function is actually a surface in the 3D space. So here is our mean squared error. This is our loss function. So this is our loss function as a function of beta 1 and beta 2, essentially, of beta 0 and beta 1. Now, let me derive partial derivatives again, right? So I already did it in the general form, so let me just kind of do it one more time so that you better understand it. Now, so this is my loss function, right? So this is my loss function. So the derivative of my loss function with respect to beta 0 is going to be what? So my loss function is the sum of many terms, right? So when I differentiate it, I'm still going to have 1 over n, still going to have the sum from 1 to n. Now I'm going to differentiate every term with respect to beta 0, right? I'm differentiating the square. So the derivative of the square is 2 times whatever is inside the square. So here is my 2. Now, yi minus beta 0 minus beta 1 xi squared. Sorry, not squared. Times the derivative of whatever is inside. So the derivative is with respect to beta 0. So the derivative of this term with respect to beta 0 is just minus 1, right? So I've got to multiply by minus 1. So I'm going to just write minus here. Okay, now let me do dl d beta 1. So in a similar way, so I'm going to have the sum from 1 to n. And again, I'm differentiating the square. So the derivative of it is going to be 2 times. So I'm going to write 2 over n. yi minus beta 0 minus beta 1 xi. And now I need to differentiate this expression inside the square with respect to beta 1, right? But with respect to beta 1, this is just a linear expression, and its derivative with respect to beta 1 is just minus xi. So I'm going to write minus in front and xi here, times xi. So these are the partial derivatives. So later we're going to implement this in R, like by hands, and see what it looks like. But now let us just see what the loss function looks like, right? So this is our advertising data set. So we have 3 axes. So our vertical axis is our loss function, mean squared error. So the 2 horizontal axes are beta 0 and beta 1. So notice that beta 0 is between changes from 0 to 10. So it's 0 here and 10 here. And beta 1 changes from negative 5 to 5, negative 5 to 5. Okay, yeah, there is a typo error here. I'm going to fix it. So it changes from negative 5 to 5. Now, what we see here is does not really look like a local minimum, right? So it seems like this whole line along this sort of a crease is going to have the same error, the same loss function. But as a matter of fact, it's not exactly like this. So the thing about it is that the level curves of this loss function are in fact very, very elongated ellipses. So instead of level curves that we typically saw in these nice plots of functions that look like this, here what we have is completely different. It's something like this. They're very, very long and very, very narrow. And we can check it by just finding this plotting these level curves. So notice that here beta 0 changes from 6 to 8, and beta 1 changes from 0 to 0.1. So the scale is completely different. So take note of the scale. And still, even if the scale is different, so we see that level curves are really, I mean, I was not even able to plot it in a way so that you see closed level curves. So these level curves, it kind of goes all the way, and it is probably 10 times like longer than here. And it is absolutely impossible to plot them nicely without doing any linear transformation. So if we do a linear transformation on beta 0 and beta 1, then we can plot it nicely. But by just stretching and squeezing these two, one of them, it's just impossible, right? So because they're slanted and they're very, very long and narrow. Okay. Now, in practice, it means that, well, our gradient descent, so it's going to look like this. So it's going to go step, 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 but then at some point it's going to turn, and is going to arrive to our local minimum. I don't know whether this local minimum is if say it is here, then it's going to kind of first quickly go into this long, very long crease, and then turn, and along the crease is going to approach our local minimum. And believe me that in practice, this is a bit of an issue with convergence of the gradient descent algorithm, and that there is a large area of computational mathematics that deals with these things, which you don't really have to know about. So you just need to understand kind of the main point is that in practice, these level curves could be very long and very narrow, and it may be a bit of an issue. Okay, so now you've seen this, so please do a little quiz.